Hello. In this video we're going to take a look at conserved quantities. So we've seen in the previous couple of videos that Ehrenfest's theorem tells us that expectation values of quantum operators give us quantities associated with the classical limits of quantum systems. So we get the classical equations of motion back on average, where average means taking the expectation value of the corresponding operator. So if we'd like to look at conserved quantities, which is generally a sort of thing we'd be interested in physics, because these are things which don't change as a function of time, it's reasonable to assume that we might want them to obey the following property. That is, we have some quantum operator A, which will have a corresponding observable quantity given by its real eigenvalue, because this will be a Hermitian operator. We take the expectation value of that for some state, and if the time derivative of that quantity is equal to 0, we call this a conserved quantity, and that should fit our classical intuition. Using Ehrenfest's theorem, we can write this as follows. So the commutator of the operator A with the Hamiltonian must be equal 0 for this to be true. That is, conserved quantities are those physical observables whose quantum Hermitian operators commute with the Hamiltonian. And this is assuming, as always in this course, that the operators, including the Hamiltonian, do not themselves have an explicit time dependence. So if this is true, just thinking of these as matrices again, which is true in many cases, otherwise they're differential operators. In either case, if we have that the two things commute, that means that we should be able to find a set of simultaneous eigenvectors for them. So we have the following. We know that this is the time-independent Schrödinger equation, so we define the eigenstates of the Hamiltonian to be n, which is labelled them by this integer n, because then we have the corresponding energy eigenvalue, E subscript n. And for our arbitrary operator A, we have, let's define this following equation. So the operator A has eigenstates, which we'll label A, and we'll call their eigenvalues A as well. As you've seen, this is quite a common notation that we tend to use. And so what we're saying is that if A and H commute, it's a general theorem which you can prove in the problem set, that you expect that it's possible to find a set of eigenvectors which are simultaneously eigenvectors of both of these operators. So we could have the following, where we've just written the state here as n comma a. So again, this is just a label. We're just labeling our states in our Hilbert space. Let's label it n comma a, but it's suggestive because then h acting on n comma a returns the eigenvalue E subscript n multiplied by the state n comma a. And a, the operator a, acting on the same state n comma a, well, that returns a times the state n comma a. Okay, so if you act, it's got these, it's a simultaneous eigenvector of both of these operators. And then this quantity A and the observable quantity, the real number A, which is its eigenvalue, will be conserved quantities. They won't be changing in time. So let's take a particular look at a particularly convenient example of this, or a very important example. Let's take the example that the operator A is just the identity operator, which acts on any state and returns the state itself. So clearly this commutes with Hamiltonian, because by definition it commutes with everything. And so therefore the time derivative of the expectation value of this for an arbitrary state is given by equal to 0. But the expectation value of the identity operator is just the inner product of the state with its Hermitian conjugate. And so we see that the inner product of the state psi with its Hermitian conjugate its time derivative is 0. But this object here is nothing other than our probability density, rewritten in terms of bras and cats. So this is just the conservation of probability, or in particular the global conservation of probability. The total probability to find the particle somewhere in the universe is always equal to 1, and so this follows. Let's take a look at another example. So our Hamiltonian in general is written as a sum of kinetic and potential parts. For the case of a free particle, by definition, the potential part is equal to 0. And in that case, we have h is the kinetic energy operator, which is just p squared over 2m, where p is the momentum operator. And so in this case, we have that the momentum commutes with the Hamiltonian, because p always commutes with any power of p. And so then in this case, we can write simultaneous eigenvectors of p and h, which we could label as follows. Where I've written the state with the label n, p, because it's going to be an eigenstate of both the operator associated with n, which is the Hamiltonian h, returning eigenvalues e subscript n, and it's also an eigenstate of p. So what this tells us is that we know that whenever two operators commute, we can have simultaneous knowledge of the corresponding observables. So in the case of a free particle, we can simultaneously know the energy of the particle and the momentum of the particle, and there's no contradiction there. We don't need to, the uncertainty relation doesn't hold in that case, because the probability of the uncertainties in two states is 0. So in general, it may not just be one operator which commutes with the Hamiltonian. We can have a larger set of operators that commute with the Hamiltonian. And it's important to try and work out the maximal set of operators which commute with the Hamiltonian. Because that set of operators, we can have simultaneous knowledge of the corresponding physical observable properties, and they'll give time-independent expectation values, so they'll be conserved quantities. So the eigenvalues of operators which commute with the Hamiltonian are called quantum numbers, and these are time-independent quantities that we can associate to the Hamiltonian, and they can all be known simultaneously. So let's look at a very important example of this. So probably the most important example we'll see in this course are the states of the electron and the hydrogen atom. So we can write these in ket notation as follows. So we have, as usual, n, the quantum number associated with energy. In the hydrogen atom, this is called the principal quantum number. And it gives us the energy eigenvalues, as usual, when acted on by the Hamiltonian. We can also extract L. So L is called the azimuthal quantum number. We'll see much more of it when we come to study angular momentum in lecture 10. And it's associated with the operator, which is the square of the angular momentum. And it returns h bar squared L plus 1, where L is an integer greater than or equal to 0. We also have the quantum number m, which is called the magnetic quantum number, and it for the z component of the angular momentum, this operator returns the eigenvalue h bar m when acting on this state, where m is an integer which ranges from -L to L. And again, we'll see much more of this when we look at angular momentum in more detail. And finally, we have S, which we've seen before, which is just the spin quantum number, where I've written it in slightly strange notation here. S is plus or minus. We could be referring to, say, the Z component of this spin, and it'll give us eigenvalues plus or minus h bar over 2 for spin up or spin down. So all of these different quantum numbers can be determined at the same time for the electron and the hydrogen atom. So we have 4 quantum numbers which will not, their expectation values of the corresponding operators will be constant in time, and so these quantum numbers are well defined for different times. So they're sensible to refer to as physical quantities. Okay, thank you for your time.